Download this code from codegive.com, link in the description below. Floating point numbers are a way to represent real numbers in a format that can support a wide range of values. They are commonly used in computer programming to handle decimal numbers, but their representation can introduce some complexities due to precision and rounding errors. Overview of floating point representation. Floating point numbers are typically represented using the IEEE 754 standard, which defines how numbers are stored in binary format. A floating point number is usually composed of three parts. One sign bit indicates whether the number is positive or negative. 2 exponent represents the scale or magnitude of the number. 3 mantissa, or fraction, represents the precision bits of the number. The general formula for a floating point number can be expressed as backslash text value equals -1 caret backslash text sign backslash times backslash text mantissa backslash times 2 caret backslash text exponent backslash. IEEE 754 format. There are two common representations in the IEEE 754 standard. Single precision, 32 bits. 1 bit for sign. 8 bits for exponent. 23 bits for mantissa. Double precision, 64 bits. 1 bit for sign. 11 bits for exponent. 52 bits for mantissa. Code example. Let's take a closer look at how floating point numbers can be represented and manipulated in Python. We'll use the struct module to illustrate the binary representation of a floating point number. Python. Import struct. Def float _to bin, number. Convert float to binary representation using struct. Packed equals struct.pack, f, number, f indicates big-endian float. Binary equals .join, f byte 08b4 byte in packed. Return binary. Def bin _to float, bin _str. Convert binary representation back to float. Packed equals int, bin _str, 2, dot to bytes, 4, byte order equals big. Return struct.unpack, f, packed, 0. Example usage. Number equals 3.14159 pi. Binary representation equals float _to bin, number. Print, f floating point number, number. Print, f binary representation, binary representation. Convert back to float. Converted back equals bin to float, binary representation. Print, f converted back to float, converted back. Explanation of the code. 1. Importing the struct module. The struct module in Python provides functionality to convert between Python values and C structs represented as Python bytes objects. 2. Float to bin function. This function takes a float as input. It uses struct.pack to convert the float into its binary representation. The result is a bytes object, which we convert to a binary string. 3. Bin to float function. This function takes a binary string as input. It converts the binary string back to bytes and then unpacks it to retrieve the float value. For example usage, we demonstrate the conversion of the float number 3.14159 to its binary representation and then back to a float. Important considerations. 1. Precision issues. Floating point numbers cannot represent all real numbers precisely. For example, numbers like 0.1 cannot be represented exactly in binary, leading to precision issues. 2. Rounding errors. Operations involving floating point numbers can result in rounding errors, which can accumulate in calculations. 3. Comparison. When comparing floating point numbers, it's often safer to check if the numbers are close enough rather than exactly equal due to potential precision issues. Conclusion. Floating point representation is a powerful tool for handling real numbers in computing, but it comes with challenges related to precision and accuracy. Understanding how these numbers are represented helps in making better design decisions in software development, especially when dealing with numerical computations. Floating point numbers are a way to represent real numbers in a format that can support a wide range of values. They are particularly useful in scientific calculations where precision and range are important. The most common standard for floating point representation is defined by the IEEE 754 standard. Overview of floating point representation. A floating point number is typically represented in 3 parts. One sign bit, S, indicates the sign of the number, 0 for positive, 1 for negative. 2. Exponent, E, represents the scale or magnitude of the number. 3. Mantissa, M, or significand, represents the precision bits of the number. The overall representation can be expressed in the following formula. Backslash text value equals, -1, S backslash times M backslash times 2 E, bias. Backslash. Where the bias is a constant that helps to represent both positive and negative exponents. For a 32-bit single precision float, the bias is 127. IEEE 754 representation. One single precision, 32 bits. 1 bit for the sign. 8 bits for the exponent. 23 bits for the mantissa. 2 double precision, 64 bits. 1 bit for the sign. 11 bits for the exponent. 52 bits for the mantissa. Example of floating point representation. Let's take a closer look at how to represent the floating point number -6.75 in single precision, 32-bit, format. 1. Convert to binary. The integer part 6 in binary is 110. The fractional part 0.75 in binary is 0.11, because backslash 0.75 backslash times 2 equals 1.5 backslash dash 1, and backslash 0.5 backslash times 2 equals 1.0 backslash dash 1. Therefore, 6.75 in binary is 110.11. To normalize the binary number, normalize it to 1.1011 times 2 3. Determine the sign bit. Since the number is negative, the sign bit is 1. 4. Calculate the exponent. The exponent is 2, from the normalization, and we add the bias of 127. Exponent equals 2 plus 127 equals 129, which is 100000001 in binary. 5. Determine the mantissa. The mantissa is derived from the normalized binary number 1011, which we fill with zeros to get 23 bits, 10110000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000Sign, 1. Exponent, 1000000001. Mantissa, 10110000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000Code example. In Python, you can use the struct module to see how floating point numbers are represented in binary. Python. Import struct. Define a floating point number. Number equals -6.75. Pack the number as a single precision float. Packed underscore number equals struct.pack, f, number. Unpack to get the binary representation. Binary underscore representation equals dot join, f byte 08b4 byte in packed underscore number. Print, f floating point number, number. Print, f binary representation, 32 bits binary underscore representation. Explanation of the code. The struct.pack, f, number, function converts the float to its binary representation in memory. The list comprehension converts each byte of the packed number into an 8-bit binary string. Finally, we print the original floating point number and its binary representation. Conclusion. Floating point representation allows a vast range of real numbers to be stored in a compact format, but it is important to remember that it comes with limitations in precision and range. Understanding how these numbers are represented can help you work effectively with numerical data in programming and scientific computing.